When I ask a question, what type of bonds are there? The popular answer would be ionic and covalent bonds. And I would be like, yeah, that's fair. For example, sodium chloride. Sodium has one electron in its outermost shell, while chlorine has seven. When they both come together, the electron jumps from sodium to chlorine to form Na plus and Cl minus. And these two atoms are held together by electrostatic attraction. For example, ethane. Ethane has CH3 and CH3, which is two radicals, and contributes one electron to this bond formation, which is shared equally, and they form a covalent bond. And here we have a symmetrical electron distribution. But what if I say that most bonds are not fully ionic nor covalent? They are somewhere in between these extremes. Such bonds are called polar covalent bonds. To understand what these polar covalent bonds are, it's really important for us to know about electronegativity. On a very basic level, electronegativity is the ability of an atom to attract the electron which is being shared in the bond. Here you see the stats of all the electronegativity of the atoms in the periodic table. The most electronegative element is fluorine, and the least electronegative element is cesium. Metals on the left-hand side of the periodic table attracts the electrons weakly and have lower electronegativities, while oxygen, nitrogen, and halogens on the right-hand side of the periodic table tend to attract the electrons most strongly. Carbon is the most important element in the organic compounds, has an intermediate electronegativity of a value of 2.5. As a rough guide, bonds between atoms whose electronegativities differ less than 0.5 are non-polar covalent bonds, whose electronegativities differ by 0.5 to 2 are polar covalent bonds, and the bonds between atoms whose electronegativities differ more than 2 are largely ionic. Charge distributions in a molecule can be displayed visually with something called as electrostatic potential maps. The electron-rich regions are indicated by red, while the electron-poor regions are indicated in blue in color. Electrostatic potential maps are useful because they not only show the regions of electron-rich and electron-poor in the atom of the molecules. With these maps, we can also correlate these molecules' electronic structure to chemical reactivity. Just as how individual bonds are polar, molecules could also be polar. A molecule's polarity results from the vector summation of all the individual bonds' polarities and lone pair contributions in the molecule. The net polarity of a molecule is measured by something called a dipole moment. The dipole moment of a molecule can be calculated by the magnitude of charge times the distance between these two atoms. Dipole moment is a vector quantity, which means it not only has a magnitude to it, but also a direction. And this direction is usually represented by an arrow. There are some rules in finding the dipole moment of a molecule. Rule number one, find the polar bonds. For each bond, look at the electronegativity difference between the atoms in the molecule. If they are non-zero, which means one of the atom in this bond is slightly electronegative and the other one is slightly electropositive. And rule number two, draw an arrow from the positive atom to the negative atom. Rule number three, add these arrows as vectors. The molecule's overall dipole moment is in the vector sum of all of its bond dipoles. When you look at these line diagrams of these molecules, although they look really simple, it's really important for us to know how to draw them properly. As for a molecule, you can draw a line structure of a molecule in a multiple ways. But what's the right way? Let's take CO2 as an example. The line diagram of CO2 can be drawn in multiple ways when you think about it. But what do you think is the right approach? Let's go step by step. Rule 1. Calculate the total number of valence electrons. Carbon is from group 14 and it has 4 valence electrons. And oxygen is from group 16 and has 6 valence electrons. So 4 from carbon and 6 from oxygen We have 2 oxygen, so it's total 12 from oxygen. In total, we have 16 electrons in carbon dioxide, valence electrons. Rule number 2, determining the central atom. The central atom is usually the least electronegative atom, or an atom which can make multiple bonds, or usually the atom which only appears once in the formula. In CO2, carbon is a lesser electronegative atom compared to oxygen, and carbon can form 4 bonds. Hence, carbon goes into the center. Connect the other atoms with a single bond. So now we have OCO. Here there are 2 single bonds. Each bond contains 2 electrons. Therefore, 2 bonds times 2 electron, which is 4 electron. Here, we started with 16 electrons and we used 4 electrons. Hence, the number of remaining electrons is 16 minus 4, which is 12 electrons. So now we have 12 electrons, which we have to distribute as lone pair to this molecule. Most atoms are stable when they have 8 electrons around them. This is called the octet rule. We normally complete these octets for the outer atoms before dealing with the central carbon atom. Each oxygen already has 2 electrons from its bond to carbon. Each oxygen therefore needs 6 more electrons. 6 electrons corresponds to 3 lone pairs. So we place 3 lone pairs on each oxygen. Once that's done, then we count on how many electrons are there on carbon and oxygen. We see that both the oxygens are being satisfied by the octet rule, but not the carbon. That can be changed when one bond from the either oxygen connects to the carbon, so it forms a double bond on both sides. Now, when you count it, each element in this molecule is being satisfied by the octet rule. Now let's take another example. Let's take the acetate ion. It's just vinegar which loses one hydrogen and has the small minus sign. Rule 1. Count the number of valence electrons. And this time we also must account for the charge. 2 carbon gives 8, 3 hydrogen gives 3 electrons, and 2 oxygen give 12. And that's total 23. And then we have a negative charge, which means we are going to add one more electron to it, which is going to give 24 electrons in total. Keep in mind, a negative charge adds an electron and a positive charge would remove them. Rule 2. Determine the central atom and connect everything. Carbon is less electronegative than oxygen, so carbon takes the central role. One carbon holds the 3 hydrogens as CH3 and the other carbon is joined to the second carbon, which is in turn joined to the next 2 oxygen atoms. And we connect everything with a single bond. Count those bonds. 3 CH bonds, 1 C bond, and 2 CO bonds. That is 6 bonds or 12 electrons used. We started with 24, so 24 minus 12 is 12 more electrons to be placed as lone pairs. Rule 3. Complete the octets for the outermost atom first. The 3 hydrogens are already finished since hydrogen only wants 2 electrons in its outermost shell. That leaves the 2 oxygen. We place the 12 remaining electrons on them. 3 lone pairs on each oxygen and all 12 are now used up. Each oxygen now has 8 electrons. But look at the central atom carbon. It only has 3 single bonds, the CC bond and then the 2 CO bonds, which is 6 electrons. It isn't short of an octet. Then we have no electrons left. So we do exactly what we did for CO2. We take the lone pair from the oxygen, move it to the bond, forming a C double bond O bond. Now the carbon has 4 bonds, a full octet. One oxygen is double bonded and the other one is single bonded and carrying this ion extra minus charge. So that is done. So we are finished with the acetate ion structure. But wait, look here what we just did. We put the double bond on one oxygen and left the negative on the other. Nothing forced us to do that. We could have easily done the other way around. Two drawings, the same molecule, the only difference is which oxygen carries the negative charge. And here's the interesting thing, right? If we measure the acetate in the laboratory, two oxygens are really identical. They have exactly the same bond length. And why do we have to choose one over the other one? Neither And that is not the failure of our rules. It is a concept in chemistry which is called resonance, which we'll be discussing in the next video.